Look up at the night sky on a clear evening, far from the glow of city lights. What you see is not the universe as it is, but as it was. The light from those distant stars has traveled for years, decades, centuries, even millennia to reach your eyes. Each photon is a messenger from the past, carrying with it the story of ancient suns, some of which may no longer exist. Some of which may no longer exist. This is the curious nature of light. It moves fast, extraordinarily fast, yet not infinitely so. And in that limitation lies one of the most profound truths about our universe. We live in a cosmos governed by rules, elegant mathematical relationships that describe everything from the fall of an apple to the motion of galaxies. Among these rules, there is perhaps none more fundamental, none more absolute than the cosmic speed limit, the speed of light. In the vacuum of space, light travels at precisely 299,792,492,282 miles per second. This is not just fast. This is the fastest that anything can travel through the fabric of space and time. But why should the universe impose such a limit? And more intriguingly, is there anything at all that can move faster than light? These are questions that go to the very heart of physical reality. They touch on the nature of space and time themselves, on the structure of matter and energy, on what is possible and what is forever forbidden by the laws of nature. To understand the cosmic speed limit is to understand something profound about the universe we inhabit, about the very stage upon which the drama of existence unfolds. Let us begin with light itself. What is light? For most of human history, we didn't really know. We knew it helped us see. We knew it came from the sun and from fire. We knew it could be reflected and refracted. But its true nature remained mysterious. In the 19th century, scientists like James Clerk Maxwell revealed that light is an electromagnetic wave, a rippling disturbance in electric and magnetic fields propagating through space. But light is also something more. As quantum mechanics taught us in the 20th century, light behaves as both wave and particle. The particles of light, which we call photons, have a very special property. They have no mass. They are pure energy in motion, forever traveling at the speed that bears their name. This is crucial. Photons have no mass, and because they have no mass, they always move at the speed of light. They cannot stand still. From the moment of their creation, whether in the nuclear furnace of a star, in the filament of a light bulb, or in the quantum transitions of an atom, photons move at this cosmic speed limit. They have no choice in the matter. It is their nature. But what about things that do have mass? What about electrons, protons, atoms, molecules, you and me? Can we reach the speed of light? The answer, as Albert Einstein showed us in 1905, is no. And the reason why opens a window into the deepest workings of reality. Einstein's special theory of relativity begins with a simple observation. The speed of light is the same for all observers, regardless of how they are moving. This seems innocent enough, almost trivial. But work out the implications of this statement. Follow the mathematics wherever it leads, and you discover something extraordinary. Space and time are not separate, absolute entities. They are woven together into a single fabric space-time. And the faster you move through space, the slower you move through time. Imagine you are aboard a spacecraft traveling at a significant fraction of the speed of light. To you, inside the spacecraft, everything seems normal. Time passes at its usual rate. But to someone watching you from Earth, something strange would be happening. They would see your clock running slow. They would see you moving in what appears to be slow motion. This is not an illusion or a trick of perception. Time genuinely passes more slowly for objects in motion. The closer you get to the speed of light, the more extreme this effect becomes. This is called time dilation, and it has been confirmed by countless experiments. Particles in accelerators, atomic clocks on airplanes, GPS satellites orbiting Earth all show exactly the effects Einstein predicted. But there's more. As you accelerate your spacecraft faster and faster, approaching the speed of light, something else happens. Your mass increases, not your rest mass. That stays the same, but your relativistic mass, the effective mass that determines how hard it is to accelerate you further. The closer you get to light speed, the more massive you become, and the more energy is required to make you go even faster. If you could somehow reach the speed of light, your mass would become infinite. And to accelerate an infinite mass would require infinite energy. The universe doesn't have infinite energy to spare. And so here's the fundamental barrier. Anything with mass can approach the speed of light, can get closer and closer to it, but can never quite reach it. The speed of light is an asymptote, a boundary that can be approached but never crossed. This is not a limitation of our technology or our engineering prowess. This is a limitation imposed by the structure of space-time itself. Think about what this means. You could build the most powerful rocket imaginable, powered by matter, antimatter annihilation, or by the energy of entire stars, and still you could not reach light speed. You could accelerate for 1,000,000 years, expending the energy output of a galaxy, and still you would fall short. The universe has set a speed limit, and it is absolute. Now, you might wonder, if nothing can travel faster than light, then is light truly the fastest thing in the universe? Are there no exceptions, no loopholes, no way around this cosmic constraint? This is where things become deliciously subtle, because the universe, while bound by rules, has a way of surprising us with nuance. Let me tell you about the expansion of space itself. When we observe distant galaxies, we find something remarkable. The farther away a galaxy is, the faster it appears to be moving away from us. This is the expansion of the universe, the aftermath of the Big Bang that brought everything into existence some 13.8 billion years ago. Now here's the curious part. Galaxies that are sufficiently far away beyond what we call the cosmic horizon are receding from us at speeds greater than the speed of light. Does this violate what I just told you? No. And here's why. These galaxies are not moving through space faster than light. Rather, the space between us and them is expanding. It's a subtle but crucial distinction. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they're traveling across the rubber, but because the rubber itself is stretching. The dots can remain perfectly still relative to the balloon surface, yet still separate from each other as the balloon expands. In the same way, galaxies can remain at rest in their local patch of space while the space between us and them grows. There is no speed limit on the expansion of space itself. The cosmic speed limit applies to motion through space, not to the expansion of space. This has profound implications. It means there are galaxies we will never see, no matter how long we wait or how powerful our telescopes become. Their light traveling toward us at the speed of light is fighting against the expansion of space, and in the most distant regions, space is winning. Those galaxies are beyond our cosmic horizon, forever unreachable, their light eternally in transit, never to arrive. The universe is larger than the observable universe. Then there is quantum entanglement, one of the strangest phenomena in all of physics. When two particles become entangled, and this can happen in various ways, but a common one involves particles created together in a single quantum event. They become linked in a way that defies our everyday intuition. Measure a property of one particle, and you instantly know the corresponding property of the other, no matter how far apart they are. Change happens instantaneously across any distance. Einstein famously called this spooky action at a distance, and he didn't like it one bit. Surely, he thought, this must violate the cosmic speed limit. If information can travel instantaneously between entangled particles, doesn't that mean something is moving faster than light? The answer maddeningly is both yes and no. Yes, the quantum correlation is instantaneous. But no, you cannot use this to send information faster than light. You cannot control what result you get when you measure your particle, so you cannot encode a message in those results. The correlation is there, it is real, it is instantaneous, but it cannot be used to communicate. Nature is subtle. She allows correlations faster than light, but preserves the speed limit on usable information. The universe has its rules, and it enforces them with ingenuity. There are other apparent exceptions, other ways the universe seems to bend its own rules. Consider something called phase velocity, a concept from wave physics. When waves travel, there are actually two speeds we can talk about. There's the group velocity, which is the speed at which the wave packet, the overall envelope of the wave, travels. This is the speed at which energy and information move, and it respects the cosmic speed limit. But there's also the phase velocity, the speed at which the individual crests and troughs of the wave appear to move. Under certain conditions, particularly in what's called anomalous dispersion, the phase velocity can exceed the speed of light. Does this matter? Not really. The phase velocity doesn't carry energy or information. It's a kind of mathematical artifact, a pattern in the wave that can appear to move faster than the substance of the wave itself. Imagine the marquee lights outside an old theater chasing each other in a circle. You could make the pattern appear to move arbitrarily fast, even faster than light, simply by spacing the bulbs appropriately and timing their flashes. But nothing physical is actually moving that fast. Each bulb stays where it is, flashing in sequence. The appearance of motion is just that, an appearance. Phase velocity can exceed the speed of light, but it doesn't violate causality or allow faster than light communication. And then there are tachyons, purely hypothetical particles that, if they existed, would always travel faster than light. The mathematics of relativity doesn't strictly forbid such particles. In fact, if you work through the equations, you find that while particles with mass must travel slower than light, and particles without mass must travel at light speed, particles with imaginary mass, whatever that might mean physically, would be required to travel faster than light. They couldn't slow down to light speed any more than we can speed up to it. But here's the thing. We've never detected a tachyon. We've never seen any evidence that they exist. And if they did exist, they would cause all sorts of problems with causality. Effects could precede causes. Information could travel backward in time. The universe would become a much stranger and more paradoxical place. So while tachyons are mathematically possible in certain formulations of physics, most physicists suspect they don't actually exist. The universe, it seems, prefers to keep things causally consistent. So what do we make of all this? We have a firm cosmic speed limit for anything traveling through space, carrying energy or information. Yet we have space itself expanding faster than light. We have quantum correlations that are instantaneous but can't transmit information. We have wave patterns that appear to move faster than light without actually doing so. We have hypothetical particles that could go faster than light but probably don't exist. The picture that emerges is one of a universe with rules that are absolute but nuanced. The speed of light is not just a speed limit for light. It is a fundamental constant of nature, woven into the structure of space-time itself. It represents the maximum speed at which cause and effect can propagate, the maximum speed at which information can travel, the speed at which the universe operates. Why does this limit exist? What is so special about 299,792,492? And the honest answer is that we don't fully know. We can describe how the speed of light fits into our equations, how it relates to other fundamental constants like the permittivity and permeability of free space. We can show that if the speed of light were different, the universe would be profoundly different, chemistry would work differently, stars would burn differently, perhaps life as we know it couldn't exist. But as to why this speed and not some other, we don't have a deeper explanation. It appears to be a brute fact about our universe, one of those numbers that is simply given. Part of the initial conditions or the fundamental laws. And yet, this limit shapes everything. It shapes the size of the observable universe, the horizon beyond which we cannot see because light has not had time to reach us. It shapes our ability to explore the cosmos, imposing vast barriers of space and time between the stars. It shapes the very possibility of science because it ensures that the universe has a consistent causal structure that causes perceived effects, that the past is fixed, and the future is open. Imagine for a moment if there were no speed limit, if information could travel instantaneously across any distance. The universe would be a very different place. There would be no concept of here and there separated by time. All events would be simultaneous. The rich structure of space-time with its past light cones and future light cones, its notion of causality and temporal order would collapse into something unrecognizable. We could not exist as beings extended in time, experiencing a flow from past to future. The very possibility of memory, of narrative, of cause and effect depends on the existence of a cosmic speed limit. So when we look out at the universe and see light from distant stars, light that has traveled for thousands or millions of years to reach us, we're seeing something profound. We're seeing the past. We're seeing the universe as it was. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light years away. When you look at Andromeda, you see it as it was 2.5 million years ago when our ancestors on Earth were just beginning to use stone tools. The light left Andromeda before we were human, traveled through the void of space for all that time, and arrived at your eye tonight. This makes every photon precious, every bit of light a time capsule. Astronomers are not just looking out into space. They are looking back in time. When we observe the most distant galaxies, we see them as they were billions of years ago in the early universe. We see cosmic history written in light. And we can do this because light moves at a finite speed, because the universe has a speed limit. This limit also imposes profound constraints on our future. If humanity ever becomes a spacefaring civilization spreading out among the stars, we will be forever limited by the speed of light. A journey to even the nearest star, Proxima Centauri, would take over 4 years at light speed, and we can't reach light speed. Any realistic mission would take decades or centuries. Communication with distant colonies would involve delays of years or decades. We would fragment into causally disconnected communities, each existing in its own pocket of space-time, unable to maintain real-time contact. Some scientists speculate about wormholes, shortcuts through space-time that might allow faster-than-light travel without actually exceeding the speed of light locally. The mathematics of general relativity permits such structures, but we don't know if they can actually exist, if they can be created, if they would be stable, or if they would be traversable. Other speculations involve warping space-time itself, creating a bubble that moves through space while the ship inside remains stationary. These are fascinating ideas, but they remain firmly in the realm of speculation. They may be impossible. They may require exotic forms of matter and energy we've never encountered. The universe may have ways of forbidding such loopholes. For now, for the foreseeable future, we are bound by the cosmic speed limit. Light speed is not just fast, it is the fastest, and that is both a limitation and a gift. It limits our reach, but gives structure to our universe. It constrains our ambitions, but ensures that cause and effect maintain their relationship. It makes the cosmos vast and mysterious, but also comprehensible and lawful. Carl Sagan, who spent his life exploring the cosmos and sharing that exploration with the world, understood this deeply. He knew that the speed of light was not just a number in a physics textbook. It was a fundamental feature of reality, one that shaped everything from the evolution of stars to the possibility of contact with extraterrestrial intelligence. When we send messages into space, hoping that someone out there might receive them, we do so knowing that any response will take years, centuries, perhaps millennia. The universe is patient. The universe operates on timescales that humble us. And there is something beautiful in that humility, something important in recognizing our limitations. We are not gods. We cannot transcend the laws of nature. We are part of the cosmos, subject to its rules, made of its substance. Every atom in our bodies was forged in the heart of a dying star, and even our thoughts, the electrical impulses in our brains, propagate at speeds far below the cosmic limit. We are, in Sagan's unforgettable phrase, star stuff contemplating the stars, temporary arrangements of matter and energy, trying to understand the universe that brought us into being. The speed of light reminds us that we are embedded in space-time, not separate from it. We cannot stand outside the universe and manipulate it at will. We are participants in its grand story, subject to its constraints, beneficiaries of its possibilities. The fact that nothing can travel faster than light is not a deficiency of the universe. It is a feature, perhaps even a necessary one, that allows the universe to be the rich, structured, causally coherent place it is. When you look up at the stars tonight, remember that the light reaching your eyes is the fastest thing in the universe. Those photons have raced across the void at the cosmic speed limit, outpacing everything else, bringing you news of distant suns. They are messengers, ambassadors of the electromagnetic force, carriers of information across the vastness of space and time. And in receiving them, in catching them with your eye and processing them with your brain, you are participating in something profound, the universe observing itself, knowing itself through the medium of light. Is there anything faster than light in the sense that matters, the sense of physical travel, of information transfer, of cause and effect? No. The universe has drawn a line, set a limit, established a maximum speed, and that limit is not just a constraint. It is a statement about the nature of reality. It tells us that space and time are intertwined, that causality matters, that the universe has structure and order. It tells us that we live in a cosmos of laws, not of arbitrary happenings, and that those laws, while they may limit us, also make possible the very existence of complex thinking beings capable of pondering such questions. So we are left with a universe that is vast beyond imagining, but not infinite in its accessibility. A universe where light is the swift messenger, but not an instantaneous one. A universe where patience is built into the very fabric of space-time. And perhaps that is as it should be. Perhaps a universe without limits would be a universe without meaning, without the precious tension between what is and what might be, without the motivation to explore and discover and understand. The cosmic speed limit is real. It is absolute, and it is beautiful. It is one more reminder that we live in an astonishing universe, one that rewards curiosity and punishes arrogance, one that is knowable but not completely known, one that invites us to keep looking, keep questioning, keep seeking to understand our place in the grand cosmic story. Somewhere, something incredible is waiting to be known, but we will discover it at the speed of light and not faster. And that journey, that patient exploration of the cosmos is part of what makes us human.